Hello everybody, this is Amir Sheikha, and today I'm going to talk about deep fusion for efficient nested recursive computations. Let's first start with the motivation. We want to write data processing pipelines such as the ones that are using machine learning, graph processing, and query processing, and we would like to write them in a high-level code. So for example, by using functional or declarative languages. And this is because usually these pipelines are implemented by data scientists who are not necessarily computer scientists with that much systems knowledge. And nevertheless, we would like to get good performance. And this is usually achieved by using code generation and compilation to generate efficient low-level code from the high-level specification of the data processing pipeline. Let's give some examples for the data processing frameworks. In functional languages such as Scala, Haskell, and OCaml, we have, in the standard library, we have functional collections such as list, which expose higher order functions such as map, filter, fold, which are basically simplifying the processing of a collection of data elements. And on the other hand, for frameworks such as Spark, they expose the notion of resilient distributed datasets or RDDs, which are very similar to the functional lists, and SQL relational databases are also exposing a declarative language called SQL, which is again has some operations like selection, projection, and join for processing relational data, and also frameworks such as Panda in Python are also exposing the notion of the data frame, which is very similar to a relation. And last but not the least, we have frameworks such as TensorFlow and PyTorch, which are exposing interfaces over tensors such as matrices and vectors for processing the linear algebra and tensor algebra data. So what is common among all these high-level abstractions is that all of them are basically processing a batch of data or a collection of data. And the operations over them are basically methods over the collections. And in most cases, actually, these operations are functional higher order methods. So this modularity and nice compositionality that they provide doesn't come for free. There are going to be performance challenges with them. So, for example, in the context of collections, all these higher order functions are basically looping over the data. And if we are not careful about them, it would lead to unnecessary loops over the data. And also, many of them are going to are going to transform the collection into another collection. And if we are not careful about that, then it's going to lead into many unnecessary intermediate collections. And to resolve this, the compilers and functional language community have worked on the loop fusion or the deforestation technique to get rid of them. So let's first start with the hello world of loop fusion, which is basically we have a list, we are doing two maps over it, meaning that we are doing a map which applies function f over the elements of the list, and then on the result of that, we are doing another map which applies function g over this intermediate list. And by writing the corresponding imperative code for this functional code, we are going to see that here we are producing an intermediate list, which here we show using temp1, and then we are iterating again over this intermediate intermediate collection in order to produce the output. So this means that here we have two loops and one intermediate collection. However, by doing loop fusion, we can basically do only a single map over the list, and we apply both functions f and g together as the input to this single map. And the corresponding imperative code for this one, as you can see, is going to have only a single loop, and there is not going to be any unnecessary intermediate collection. So this was one example of loop fusion. We have another example of loop fusion as well. Let's consider the case where we are interested in computing the average of numbers stored in a list. So in order to do that, first we are summing over all the elements, and we are counting the elements of the number of elements of the list, and then we are dividing the summation by the count. So if we naively translate this into some imperative code, we are going to iterate over the same list twice. In the first iteration, we are going to compute the result of the summation. In the second iteration, we are going to compute the result of the count. And then at the end, we are dividing the result of summation by the count. So here we have two loops. However, we could have a better implementation where we are using the fold left method in order to iterate over the list once, and we actually create a tuple, the first element of which is the result of the summation, and the second element is the result of count. And then we divide the first element by the second element. And here you can see the corresponding imperative implementation. So here, to make it even nicer to show, we are getting rid of the intermediate tuple abstraction as well. And here the good thing is that we have, instead of two loops, we have only one loop. And in this work, I'm going to show yet another version of loop fusion, where we are starting from a nested invocation of flat map, where we have basically two lists, list 1 and list 2. And what we are doing is that we are basically doing the Cartesian product of the elements of the list 1 and list 2, where we apply basically function f over each pair of the elements that we see. So the corresponding imperative implementation is going to be as follows. And if you see here, we have basically one intermediate collection inside the outer loop, which is basically this variable tmp that you can see here. And so, but first we are iterating over the outer list, and we are allocating this intermediate tmp, where the elements are basically appended by this function f of x1 and x2. And at the end, we are basically appending all those elements to res. So instead of this, we could have a more efficient version where we don't allocate this intermediate collection. And instead of that, we immediately append the elements to the output result. And the advantage of this one is that there is not going to be any intermediate collection anymore. And in this talk, I'm going to show you how should we represent the corresponding high-level notation for this program and how we should achieve this optimization. So basically, we have seen different categories of loop fusion. The first kind, which was the hello world example, was achieving vertical loop fusion. The second kind was achieving the horizontal loop fusion. And the third kind that we introduced in this paper is achieving deep fusion, which deals with fusion for nested recursive computations. So one question is that, where does the nested recursive computation appears? So here we have seen an example for processing nested lists that it could have appeared. But also the other example is whenever we are doing computations over sparse tensors. So for example, we are doing sparse tensor contractions. And the other example is basically in the context of query processing for doing special kind of joins, which are called worst case optimal joins, which are basically represented as nested loops. So let's give the execution trace for our running example, which is again this nested flat map. So let's assume that we have list 1, which has object 1 and object 2, and list 2, which has object 3 and object 4. So the execution trace is going to be as follows. So we have basically the outer result, which is res, and the intermediate collection, which we called it temp. And first, we are actually appending the elements to temp, and then we are appending the result of temp to res, and then again, we are doing the same thing for the next set of elements. And instead of this, we wanted to get rid of the appending to the temp and immediately append everything to the res. However, if we observe it from a more mathematical point of view, and if we name the intermediate list as A, B, and C and D, we actually observe that the left one corresponds to the following appending of list, and the right one corresponds to a completely different way of organizing, of association of append. And basically, in order for these two to be equivalent, we need to use some sort of mathematical properties. The mathematical properties that we care about here is the unit property, where there is basically a zero element or the unit element that whenever we are appending, it basically is like not doing any append. And the associativity is that, okay, the order in which we do the append doesn't really matter. And the commutativity is that whenever we change the operands for the append, it doesn't matter. And the idempotence is that whenever we append an element by itself, at least let's say a collection by itself, it doesn't change anything. So, and here, in order for the left-hand side and the right-hand side to be equivalent, it's basically using the associativity feature. So here, by naming appending of A to B as E, you see that by one round of associativity, we can reach to the from the left one to the right one. And inspired by these mathematical structures, there is a well-known hierarchy for collections called the Boom hierarchy for the collections, based on the mathematical properties that they satisfy. So the tree collection basically only has the unit property. The list, in addition, has the associativity. So the bag, in the bag, you can think of it as an unordered list, and set is when the duplicates do not matter, and because of that, the idempotence is also supported. As in this work for the optimization that we have said, we only care about associativity. We only consider the collections of list, bag, and set where the associativity feature is satisfied. So what is the mathematical construct that captures the unit property and the associativity? That's basically the monoid structure. So the monoid basically has an operation op and an element unit, where we basically have the associativity and the unit feature for these two constructs. And what are the monoid collections? They are basically collections with a monoid structure with a particular operation called a summation, where whenever you give it a particular type, which is a monoid, and you apply a function f, which returns an object of that type, which is actually a monoid type, it's going to basically apply the monoid operation over all the elements. And basically, by implementing list as a monoid collection, we can implement all of the higher order operations of a list in terms of this single operator. And in order to support sets and bags, we use a monoid dictionary, which is basically a dictionary which in the values also form a monoid. And by this we can represent sets, bags, sparse vectors, and sparse matrices. And you can refer to our UPSLA paper for more details about such a structure. So going back to our running example, we can represent the nested flat map as basically a nested sum. And now, in order to convert it in order to apply the optimization, first we would like to introduce the notion of the destination passing style representation, which is actually a representation where we pass the destination memory as well. So, for example, for the summation, we instead of that, we rewrite whatever summation that we use in terms of the DPS variant of the summation, where we are passing the destination as well. So in our running example, basically this nested summation is going to be translated into the following code. And note that here, during the DPS translation, we are going to have these, we are going to introduce this intermediate temporary destination. However, we can now reuse this temporary destination. And by reusing that, we basically can completely get rid of the unnecessary intermediate collection. And apart from that, if we see here, we are also introducing a singleton collection which can be removed. And by removing that, we can reach to the following program which has no intermediate collection. And just to showcase for a result, I'm showing you here the sparse matrix transpose, where you can see that by applying both these optimizations alongside DPS, we can get up to 4 times performance improvement over the standard implementation provided by the Scala library. So to summarize, I've shown you the deep loop fusion technique, which basically is going to remove the intermediate collections that are introduced in nested recursive computations. And I've shown you that in order to do that, we need to rely on the associativity feature of monoid collections such as lists, sets, bags, and tensors. And in order to do that, I've introduced you the destination passing style technique that has been used before in order to convert functional code into imperative code. But I've introduced 2 versions, 2 optimizations, where we can reuse the destinations in order to get rid of these intermediate collections in a coarse grain level of granularity, and also removing the singleton collections that are constructed in order to apply an optimization in the finer level of granularity. Thank you so much for your attention.
Thanks. Now we can take questions and have Amir answer online. How much? Do you have any questions?
Maybe it's a good idea to say your name first.
My name?
because the speaker can't see you.
Is the microphone?
I think is the microphone work? Can you speak up?
Okay. So do you hear me?
I think so.
Thank you very much.
The mic doesn't work.
Doesn't work. Do you hear me? Yeah.
Or you can come up here.
I mean,
I hear, but the voice is very low.
Maybe you type the question.
or you can come. The wireless microphone doesn't work very well.
So we should ask questions here. So thank you very much for a very interesting talk. And I'm curious about two points. And why is that? So your evaluation is a little bit, very simple one. And so it seems that so your technique can improve a lot of things. And can you show us a bigger example or bigger successful use case of your technique? Do you hear me? Oh, he's considering, I think.
Yes, it has been used in SDQL,
Uh-huh.
which will be presented at
I
the
see.
main conference.
We should attend. Okay, I see. Thank you. Yeah.
In the DBML workload.
Okay. Yeah, so the second question is a very small point. You mentioned that in the middle of your presentation, you mentioned that it is worst case optimal joins or something like that. I'm curious. Of course, we are interested in average case optimal, average case improvement or for join operation. Can you explain a little bit more about that point?
Sure. Maybe you'll ask, will you please? Worst case optimal joins are relatively new in databases.
Yeah, we need speech recognition. In triangle queries, they give better computational complexities. From O(n) squared to O(n) to the 1.5. Their implementation goes beyond normal hash joins. And requires nested computations. That is where deep fusion can become very useful. I see. Thanks for the question. Okay.